Okay, so on the limit. This is for YouTube or from what?
This for you.
YouTube. So it's online. It's like
We every day, like this is the recording that is available on YouTube. There is one more which has a good quality, better pointer one can see. Which is for that. And it especially goes on TLC channel, teaching learning center.
so do you remember where did we stop on Friday? Optical clock. So I was just introducing like what is the advantages of the optical clock and different kind of forbidden transitions. Those are used for optical clocks. So some example of the forbidden transitions. I told you the three different forbidden transitions. One, yes, so quadruple transitions, octuple transitions, hyperfine transitions, and it could be much higher orders also. But even octuple transition, driving that transition is extremely hard. So people have not seen any transition beyond octuple transitions. There is another kind of transitions people are looking for, that is nuclear transitions. Well, nuclear transition is very known, but that's in the gamma range. But there are few elements where there are nuclear transitions in the optical domain. For example, thorium-229 nucleus is a very unique nucleus which has a transition in nuclear transition, not electronic, which is in somewhere between 100 to 200 nanometer photon. It's not known exactly where it is. And a big effort is going on in few places to find out that transition, and it should be somewhere on that range. So the next generation optical clock, which will have at least 2 orders of magnitude better sensitivity, will be based on nuclear transitions, and thorium-229 is one of the very potential candidate for that. I will not discuss those, just I have a minute to start, so I'm saying. Okay, now let me start. So today I will be mostly talking about the different type of optical clocks. Particularly, there are two different types. And actually, by the way, I am actually going very slow compared to what I thought, but that's okay. I mean, I will try to go as far as possible, but I don't want to go in very hurry because then you will not be able to understand. It's better that you understand little, but you understand in a very good way so that you can there is some take-home message. Other than it's not giving a presentation. So it's like really the aim is that you get something, some knowledge and bring it back when you are going back from here. Okay, so there are two types of optical transitions. Forget about nuclear transition at this moment. So two optical transitions, optical clocks. Those have been realized quite a bit in two places in the world. And one is based on neutral atoms, and the other one is based on ions. So what does that mean? Basically, there are optical transitions which can be used for clocks. That means these are forbidden optical transitions. And that's an electronic transition basically. So these electronic transitions are available in neutral atoms as well as ions. But in terms of technology, from the clock's point of view, it's an forbidden optical transition, and you can find it in any element like that. And there are two categories of element. One is neutral atoms, and other one is ion. But for the experimentalist point of view, two different things are very much different to achieve technologically. Because for neutral atoms, if you have to cool or trap and cool, then what technique you use? I described magneto-optical trapping, laser cooling, these things. But for charged particles like ions, you cannot use magneto-optical trapping. Well, it's not entirely true. You can probably use magneto-optical trapping, but charged particles are much more energetic, So magneto-optical trapping is not an efficient technique for that. But see, charge particle has a charge. So the better to use some Coulomb force, some electrodynamic force to trap it instead of force from the photons, which is very tiny in that sense because each photon is carrying very little momentum. So it's better to use electric fields or magnetic fields to trap charge particles. It's much more efficient. So now these two techniques are very much different in from an experimentalist point of view. Two systems are completely different. Technologies are completely different. And that's why, based on technology, this is categorized into two different things. One is neutral atoms and one is trapped ion things. And today, my focus will be practically describing these two techniques. Okay. So, okay. So, like, let's first try to understand from a technological point of view what is required to build a clock, to build an atomic clock, optical atomic clock. So the first thing is you have to have a system, and this system would be one of these two, which I just showed in the last slide, like trapping neutral atoms or trapping charged particles and cooling them to some sort of lower than millikelvin temperature, right? So you prepare your sample. The first thing is you prepare your sample, and that sample is either charged particle or neutral atom. So that's in this blue box. Second thing is what you need? You have to drive that transition, clock transition, and this clock transition has a line width of very narrow, like some are in the order of hertz or even lower than hertz. So you have to prepare the laser light in such a way the laser which you are using to interpret this clock transition has similar sort of transition, line width and stability. So a typical commercial laser, if you buy a very good quality commercial laser, it has a line width of 100 kilohertz. But that's not useful because if you have a 100 kilohertz line width and using that you are trying to measure a very narrow line width which is 1 hertz, you will be limited by line width of the laser. There is some noise online. Santosh, can you please check it? So that means you have to bring down the line width of the laser to hertz range or maybe even sub-hertz range. Then only it is useful. So, and that is something not commercially easily available. That you have to build, this technology you have to build in the lab, and that's very complex technology. I won't go into that detail of this complex technology, but maybe when you have a lab visit today, the students can tell you a little bit on that side. So that means the second thing is this preparation of the, this one, second stage is preparation of the clock laser, which satisfies the Santosh? I'm calling. Huh? Yeah, can you please ask? So you have to prepare the laser which satisfies the criteria that you need to drive your clock transitions. Okay, so that is this step 2. Then using that laser, you can drive the transition and you can sort of measure this Lorentzian line shape, and then you can find out, okay, this is my centroid frequency where the amplitude becomes maximum, and so on, which I described on my very first or second lecture, something like that. But still, one thing is missing in these things to make it as a clock. What is that? Just guess. This is general, like your thought process. You have the system, which is ions or atoms. You have the laser. You use the laser to drive the clock transition. You measure the sort of Lorentzian line set. Then you know what is the center of the frequency and etc. But which is missing still? How do you know which frequency is that? It's not that the transition frequency of the things is known. I mean, how do you know in first place? Well, of course, one can say theoretically, one can find it out, but theory is theory. It's not. It has some uncertainty and big error, but theory can do a mistake. So you have to synthesize that frequency. Like I am driving a transition which is something like, let's say, 632 dot some numbers dot, and after decimal point there are few dots, and you want to know this frequency with a resolution of something 10 millihertz. How do you know that frequency? So that means you have to have a mechanism to find out that frequency independently, and that is called frequency synthesization. Probably, I don't know whether you have done something RF experiments or radio frequency experiments, probably you have not done. So you have to have a right characterization tool to find out, okay, this is my transition frequency that I am measuring. So for that, so in radio frequency, this is called RF spectrum analyzer, which does this characterization of the RF frequency. But in optics, in optical wavelength, that's very difficult. And then well, it's not difficult, means different type of techniques are used. And there we have to use optical frequency comb. And that was a Nobel Prize winning technology. Ted Hans in 2005, and with two other colleagues, Harosh, and what was the third one? I forgot. These three gentlemen got Nobel Prize on uh, discovering of this very efficient technology, which is called frequency comb. What is frequency comb? What is comb? You know comb, right? So comb में क्या होता है? You have these sticks which you use for combing. So that's how the name actually came. This is also a special kind of laser where you have many outputs at different wavelengths. So this axis is what you see here basically, this is. So this axis is frequency or wavelength, and these are outputs of that laser, and zillions, not a single output. Otherwise, a laser has a single output at a single frequency, right? But in this case, you have multiple outputs, and the good thing is all these outputs are equally spaced. That means this output and this output, this is, let's say, some frequency difference, let's say it's 200 megahertz. So then all these outputs have exactly 200 megahertz frequency difference.
Millihertz.
Sorry?
Millihertz.
Huh?
Millihertz or megahertz?
Megahertz. Frequency difference is megahertz, hundreds of megahertz. It's
each output.
Between each outputs, yeah. Now, well, this is not really true. I mean, nothing can be exactly separated. No? Nothing can be exact. So, what are the two instabilities it can have? Let's say this is my finger, these are the teeth. So, what are the two sort of instabilities it can have? It can move like this, and it can also move like this, right? So, these are the two instabilities. But using this frequency of reference, you have now an atomic reference, atomic transition frequency as a reference. You can practically stop both of these motions. This is common mode motion, and this is differential mode motion. And you can stop both of these motion, and you can really, well, again, really means something very small deviations. And then one can find out, there is a technique, I am not going to technical detail, to find out what is the start frequency f0, and one can count how many ticks away I am. So my transition frequency, let's say this is a transition frequency which I am using to drive the clock transition. Then one can find out, okay, this tick is n numbers of ticks away from my starting point. So n times frequency difference between these two ticks plus f0 is your absolute frequency of that transition frequency. Well, but what I am telling you, I am actually telling you very roughly. The technology is a little bit more challenging, but I don't want to go into really deep into that technology because it itself will be few lectures. So, but you understand the technique. Like, let's say I know what is my f0. There is a technique by which I can find out f0, and then I can find out. I know exactly that which tick is corresponds to my transition frequency for these atoms or ion chains. Then, if this is nth tick, then n times frequency difference between both of these, which is fr plus f0, is my transition frequency, which I have synthesized independently. Okay, so then by this entire technology, I can tell you that what was exactly that centroid frequency that I measured from that Lorentzian set. Now you have a frequency reference. Okay, then you can use it as a frequency reference. And frequency reference is nothing but like inverse of that is the one can convert it time. Okay. Now to do it in the lab, if I separate out the required work in terms of sort of let's say complexity of the things, then there are 5 different things one has to do in the lab, 5 different treatments. Each of these things, each of these boxes, what you see, these are quite complex and it's like multiple PhD thesis. So it's not something like each box is just one day or something. Okay, so the thing is, first one has to produce these lasers which has the right stability and criteria, line width, all these things. It itself is a very complex technology. The second thing is you have to prepare the system. For us, this is ion trap. One can also use neutral atom. So that's why here it is written ion trap, but it could be neutral atom optical lattice as well. This is also again very complex technology to like you have to do the technological development in the lab. It's not something commercially available. You just buy it from the market and put it on your lab. Okay. The third thing is optical frequency synthesization, what I described you, like using the frequency comb and etc. So the frequency comb is commercially available, but just buying the frequency comb is not enough. Why it is not enough? Because you have to stop these two motions, and that you have to do it in your lab. And second thing also, there is another thing like frequency down conversion or up conversion, depends on your clock transition, it's required. So that also one has to do it in the lab. So again, this is the third part, which is very complex, which one has to do in the lab if somebody wants to build the clock. Fourth thing is this optical fiber phase noise cancellation. What is that? I did not describe that actually in the last thing. Like you know the standard fiber optic communication, right? That is used for our 5G and all this network. So what happens? The 1550 nanometer light is carrying actually your data or your classical data. It goes to the fiber, it goes to the other end, and it comes to the user. But in this case, what happens? The fiber length is not constant. Fiber length is always changing. Why it is changing? Why it can change? Have you seen optical fibers? No. Okay. Huh? Okay, today you will see in the lab. Okay. So, so the length of the fiber is never constant. Why? Because of the temperature. Temperature is changing, and a little bit temperature change will change the length of the fiber. Expansion and contraction. Also stress. If you put stress, anybody have read the nonlinear effects? Kerala, very nice place for nonlinear optics. Okay, anyhow, due to stress and strain, it changes the birefringence property of any materials, and that changes like polarization shifts or basically the light which is propagating inside of the fiber, they come at a random pace. So basically what I'm trying to say, this normal classical fiber, if you put a photon which is let's say at a perfect frequency and phase, at the end of the fiber, you will find these photons at a random phase because its length changes. Okay, why that is the case? Because let's say this is my fiber, and the light is propagating like this. So sometimes the photons are coming at this phase, but sometimes this fiber length extends. So then photon comes at this phase, roughly speaking. Right? So that means at the end, you will always get these photons at a random phase for a normal classical fiber. And that is not acceptable for clock applications because the entire thing what we are trying to get is stability. So two things in the clock in the first day I described. What are the two requirements? One was stability and yeah, so the counter has to have a stability. Sorry, pendulum has to have a stability and counter has to have a repeatability. Okay, so that means for stability reason one has to stabilize the length of the fiber also. And this fiber length is like from here to some international, some other country. It could be, or it could be just next lab, or it could be somewhere else in a different city. So like we are talking about few meters, 5 meters to maybe 5,000 kilometers. So one has to have it develop the technology to stabilize the length of the fiber, and that's again very critical thing. And the fifth thing is the entire experiment. There are many free parameters, like there are many knobs. For example, we are using let's say 20 power supply. So 20 power supply have different knobs to control voltage, current. Then there are many other optics, etc. So there are like thousands of things which have to control, and we should not control it should not be human control. It's just impossible. So everything has to be automatized. So practically what you want at the end, you should be sitting at your home from your iPad or computer, you should just click one button and the experiment should start and stop itself, take the data. Because even the human is inside the lab when you are doing the experiment, it would change the parameters, temperature of the lab and etc. etc. So practically we want to build the experiment in such a way that there is no human being or no one inside the lab. So everything has to be computer controlled, remote controlled. So that is again another challenging thing, and that is called computer controlling of the entire experiment. So these are the 5 different building blocks in general thing which one has to customize in the lab, and that's challenging, but that's not impossible. That's why actually like your interest should come that I want to do that thing. Nothing is, I mean, these are difficult but not impossible. People have done that, so it's possible. And this is what I want to emphasize at this point. Like so far, up to BSc, MSc, you just study something in the lectures and etc. And most of the time, you are not able to connect what you are studying to an application. For example, you study op-amp, you just mark out 5 different criteria of the op-amp, but you don't know how to use an op-amp to make an, let's say, amplifier circuit. But that's where actually your basic knowledge, what you are studying right now during your BSc and MSc levels, these are the only things required to develop all these things. Nothing more is required. Rest of the things are, you can actually just slowly learn. So don't get worried that, okay, I don't know, these are so complex technologies, how can I do that, etc. I have never seen a fiber, I have never seen a laser, etc. The only thing what you have to know, the principle of the laser. And if you know that thing, then you know how to use that thing for some particular application. So don't get frustrated, okay, this looks like very complex. No, it's not. Everyone starts exactly from like you, PSc, LSC, and study the basics. So my request is please clear your basics very clearly. If that is clear, then there will be no problem. Okay, now I will spend a little bit of time to explain the trapped ion things, and then after that I will explain the trapped neutral atom things. Okay, so this is just a pictorial representation of the trapped ion, but let me just go to the next one. So the person who first thought that ions can be trapped in an electrodynamic force using an electrodynamic force is Penning. And he had 2 students, Wolfgang Paul and Demel. He actually sort of did the basic building blocks, which is basically required. But then actual trapping was demonstrated by these 2 gentlemen, Wolfgang Paul and Demel. And they used 2 slightly different techniques for trapping ions. And it's named the one technique which was developed by Wolfgang Paul is named as Paul trap. And the other technique which was developed by Hans Demel, he actually gave the name of the trap in the name of his supervisor, and it's called Penning trap, because Penning is the pioneering of this entire thing. Okay. And the difference of these 2 techniques, I'll come into detail, is, I mean, in this case, what you have to do, I mean, for trapping an ion. So ions have some kinetic energy, so it's not trapped in general, it's just flying over. So you have to create a 3D confining potential in all 3 dimensions, so that the ions can stay in that 3-dimensional confining potential. That's the whole thing is required. And for Paul, he used an oscillating electric field, like an AC electric field. I'll come into little detail of that. And Penning, he used a DC electric field plus magnetic field. And why that is the case, I will explain that. And that's how these two different type of traps are named as two different categories as Paul trap and Penning trap. So, but basic is both of them use some electrodynamic force. Okay, one is AC electric field, another one is DC electric field plus magnetic field. Okay. So let's just go into a little bit of simple mathematics. So force, which is m times acceleration, mass of the charge is m, is equals to what is the electric force? It's charge times electric field, the force balance. And electric field is negative gradient of the potential minus gradient of phi, and phi is the trapping potential. So you have to create a phi which is in 3 dimensions, all 3 dimensions. Then negative gradient of that will give you a 3-dimensional force. Okay. So let's take the simplest one. Phi is in the form of, it has a radial symmetry. XY is, let's say, the radial plane, and Z is perpendicular to the radial plane. So it has a radial symmetric. Alpha is some constant, and x square plus y square, plus beta is another constant. So alpha and beta, two are different things, two different constants. But there is a difference in sign also, right? There is a minus sign here in front of alpha, but there is a positive sign there. So what is this type of potential? No. If it is quadratic to position, what is it called? Harmonic. No? Trapped particle in harmonic potential, this is a BSc thing. Okay, so this is a harmonic potential. So if you take a negative gradient of that to get the force, then you get plus sign here in this force and you get a negative force here. So negative force is what? I explained it in the magnet-optical trapping. Negative force is actually confines. What is the meaning of negative force? What is the meaning of this negative sign? Sorry, you are saying something. I cannot hear. Can you be louder? Not center. Directions against the velocity movement of the particle. Center is something you define. I can say center is somewhere in Kanpur. You know, there is a place in Kanpur which is called center of the universe. That's why I took this example. Yes. Well, it's a meat. So that's why I bring it up. So that means in this case, if I take this potential of this form, only along one direction I can get a confining potential, but in the other direction it's a deconfining, the deconfining part. That means it will push the particle along its velocity. That's not what we want. We want a 3-dimensional confining potential. So that means if we take an electrostatic force, this is an electrostatic force, it's constant. Dynamic, there is no dynamicity in this. That means if you take an electrostatic force, you will get a confining force only along maximum directions. The third direction will be non-confining. That means there is no global maxima or minima. There is only local maxima or minima. What is it called? You have learned it in mathematical physics. Saddle point. You guys should say something. Maximum minima to किया है ना mathematical physics में. So if you get a local maxima or local minima, but not a global one, it's called saddle point. So that means if you take an electrostatic force, you only can get a saddle point, and so that's basically how one should connect what you are reading in your textbook to an application level. And this is a classic example. See, I am sure you have learned the saddle point things, but this is exactly the application what you see here. So now, if you have a saddle point, you cannot confine things in all 3 directions. You can confine only along maximum 2 dimensions, but the third dimension will be always be confined. It's not, it doesn't work. Well, then what you have to do? You have to do something to this so static electric field cannot be used. Okay, what you can do? Okay, that's what basically it says. So the potential, if it is a saddle point, the potential, it look like a potato chips. It's a potato chips, right? Lays. So in this direction, this is confining, it has a local minima, the ion will be staying here, but this direction is deconfining, this is maxima, right? You understand? This is the 3 dimensions, and this is the potential which I have plotted. So along this dimension, the ion will be trapped here, but along this dimension, ion will fall from this side. So potato chips won't work. What do you have to do? What could be the possible solution for this? Yeah? You are saying something. Just say no problem. Doesn't matter it's wrong or right.
So we have to confine the direction.
Yeah, but how can you do that? That's the whole point. You can rotate the potato chips very fast. Okay, so let's say this is the axis, and along surrounding to this axis, you can rotate the potato chips very fast. Then what will happen? Whenever the ion will try to fall from this side, this potential will be rotated, and it will see a confining along that direction. Again, when it will try to fall down from the other direction, it will rotate. So the rotation has to be really fast. Then on a time level, how fast it is? The rotation has to be, the ion has some motion. Let's say it's oscillating motion. So ion is trying to fall from this side and then again going into that direction. So you can plot it in first order, something like a sinusoidal function. So the rotation frequency has to be much faster than the sinusoidal motion of the ion. So that on a time average thing, ion doesn't see this deconfining part, it only sees a confining potential. Right? Now how can you rotate this? What can you rotate? You can rotate the potential itself, right? Or you can rotate the ion. Both is possible. So how can you rotate the potential itself? Instead of a static electric field, you take a dynamic electric field, an AC electric field. AC electric field में क्या होता है? Phase change होता है in every half of the cycle. So that means you have to take a radio frequency जिसका phase change होता है on the order of 10 megahertz frequency rate में, and the oscillating this potential will look like a time average 3D confining potential. What can you do for? Okay, that's what is basically written here. So this is what it is like. This is the first one. And how can you rotate the ion? It's already written, but you can explain. Yes. So you can apply a magnetic field, and then what is this formula? Q into E plus V cross B, Lenz's force. Yeah. So for this velocity in a magnetic field, it will be the cyclotron motion, and if you choose a magnetic field correctly, then the ion will be circulating very fast. So ion itself will see, okay, no, I cannot fall because it will rotate itself. So that's what is basically drawn here. So this is the cyclotron first. And other one which I just explained you, what happened? This is like that. So you change the potential itself. You change the direction of the potential itself. So the oscillating potential. So this is in an AC electric field. This is in a DC electric field plus magnetic field. So this is actually simulated. Okay. And the ion motion is basically plotted here, but let's not go into that. So today I will be focusing on this Paul trap, which uses an AC electric field. And because the iron clock particularly uses a Paul trap, why it doesn't use a penning trap? Just from your general knowledge. Because in the penning trap you have to use a magnetic field, and in a magnetic field there will have a Zeeman shift of the transition. And Zeeman shift will shift your transition frequency. Let's say the frequency in an unperturbed condition, that is the clock frequency we are talking, is nu zero, but due to Z1 shift, it will be shifted depending on magnetic field. So you will not be able to measure the exact unperturbed frequency. That's why in the for clock application, people use the fault track, not the penning track. Okay, and that's why I will focus only on the fault track. So I started with this kind of harmonic potential, which was sort of static. But then if you choose in such a way that minus and plus sign alters in half of the cycle, that's what AC field is, right? You are following or no? If you are not following, please stop me because I will be able to explain that thing maybe once more. Okay, so you due to AC field, this plus and minus sign just alters in half of the cycle, and that's why it creates this kind of oscillating potential. Okay, this is just mathematics, let's not go into that. And then the ion will be trapped. But even the ion is trapped. So this is actually a thing which is shown. The ion initially gets trapped, but then it has a lot of energy. You have to then cool the ion to get it to take its energy away, kinetic energy. And once you take its energy away, then it will practically, it has a very little energy to start with, and it will sort of stay at the very center position of the ion track. And you see these colors are changing, basically that means the polarity is changing, its phase is altered. Okay. Now, again, coming back to this equation of motion that I have explained, now your phi is dynamic, it has a time dependent property, and you choose your phi, what happens is like that. It has a DC electric part and an AC electric part. DC, forget about the DC part right now, this is just you need little bit of DC sometimes. So basically it has a AC electric part, which is V times cos, omega is the oscillating frequency, and times t. You are following this thing. This is very simple mathematics equation of motion. Okay, and then due to these three directions, x, y, z, you are just writing it in terms of this matrix form. Now one can write this x, y, z in a as just simplified version in terms of u, where u means x, y, z, and then this rest of these things, which one part is depends on the DC part and other part depends on the AC part, one can write in terms of two dimensionless parameters A and Q is J subscripts just like XYZ basically. So we are introducing two dimensionless parameters A and Q. You don't need to remember this part that much. Just try to understand. Yeah, okay. Because I will come to another phenomenon of it. That's why I'm explaining, but need not to remember. Just get a feeling. So this A, since it's radially symmetric, AX and AY will be same, and AZ is different. There is a factor of 2. You see, there is a factor of 2 here. So there is a factor of 2 difference there. A depends on the DC part of the electric field, and Q depends on the AC part of the electric field. Okay, and this A, Q both are dimensionless. And then if you do a little bit of mathematics, then you can write the generalized solution of this XYZ, okay, path of the ions. Okay, you don't need to remember that thing, but just remember there are two dimensionless parameters we are defining A and Q. A depends on the DC part, Q depends on the AC parts. Now the important part what I wanted to describe is, like if you plot this Q versus A for any directions, X or Y or Z, then you can get this kind of plots. Okay, so this blue one is for, let's say, Z direction, and red one is for X or Y direction. Like red one is for radial direction, and blue one is for the axial direction, which is Z direction. Now A and Q, this is a phase diagram. You see only at certain points they overlap each other. And in rest of the place, for example, this one, they are not overlapping. Only on certain points, their blue and red plots, they are overlapping on each other. What does that mean? This is called stability diagram. That means if you choose your AC or DC electric field, which are is nothing but Q and A, in some cases, there are most of the cases where it might be, the ion's path might be stabilizing one direction, but not on the both direction at the same time. only on those parts where they are overlapping. If you choose your A and Q parameters or AC and DC electric fields in such a way that they fall on these overlapping places, then only the ion will be stabilized along both X, Y, and Z directions. So that means what do you want? You want to stabilize the ion in all three directions. So this part is basically zoomed in here, and you have to choose your A and Q parameters such that it falls into this thing. So it's not that you take any AC electric field or any DC electric field, combine them and the ions will be trapped. There has to be only certain combinations where it can be stably trapped along all three directions. Okay. What is this? Okay, this, let's say, yeah. So this adiabicity, let's say, let's not go into that thing. But again, I'm writing this U in some little bit more simplifying, after a little bit more simplifying. And the simplification is basically I have taken adiabatic approximation like the energy conservation during the one cycle of its motion. Let's but forget about that at this moment. And if you consider that, you can simplify the equation of motion a little bit further, and you can write it in two cosine terms. And this cosine term corresponds to micromotion. This cosine terms gives one type of motion to the ion, and that is called micromotion. And this cosine term gives another type of motion to the ion, that is called secular motion. Now, the thing what you should look at what is this omega? What was that omega? That omega was the frequency of the radio frequency that we applied. Okay. We applied the radio frequency on the order of 10 megahertz, sort of that range. So that is to rotate the potential very fast. That's this frequency, omega. Whereas beta, for this adiabatic condition, is a much smaller than 1. So that means this cosine part, this frequency, this is again another frequency, beta times omega by 2. That is much smaller compared to the omega, that is the radio frequency. So one is so the take home message is ion will have one motion which is very fast, which corresponds to this cosine part, and ion will have another motion which is rather slower. Okay, so the micro motion happens at a much faster time scale, and secular motion happens at a much slower time scale. Just remember these things. You don't need to remember the mathematics. That's something not really required at this moment. But I wanted to basically bring that these two type of motion, one is happening at a much faster time scale, at the same time scale that you apply the RF, and another one happens at a much slower time scale, that is called secular motion. Now, for this point trap potential, if I plot its trajectory, sorry, what happens? Yeah, this should plot. There is a move. Okay, anyhow, it doesn't happen. So let me just go. So you see, there is one motion which is this path. This is called secular motion. This happens at a much slower time scale. But then on top of that, the secular motion gets modulated at much higher frequency. This is called micromotion. And one can really, this is a numerically calculated thing for particular conditions. We have calculated for our ion trap. The trajectory, the blue and red is again Z direction and radial direction. You can see this is one sort of oscillations or motion, and this is called secular motion. And if you look very carefully on a smaller portion, zoom some portion of it, then you will see there are a lot of high frequency oscillations in it, and you can extract them, and this is called micromotion. Is that part clear? That you have so you don't need to remember all these plots and etc. But basically the simple ion trap dynamics I tried to explain. So there is yeah.
Since the oscillating electric field, there was a plot which said the confinement direction is changed in Z axis. Doesn't it mean that it is oscillating?
It is oscillating along all three directions. See, what is your question? Sorry, can you repeat?
In the simulated thing,
yeah.
As we rotate the potential, then the confinement direction changes.
Very fast, right?
So is it not oscillating?
It's oscillating. That's why you see. The ion is when it is trapped, within the trap, it is oscillating. It's never staying fixed at a point. Okay, it is oscillating. And that's what you see in the, that's what like I try to derive its motion trajectory, and you see the motion is actually oscillating. There are two cosine terms I showed you. It says it's oscillating. Nobody is denying it's not oscillating. No, sorry again. I mean, is that what your question or what was?
If it is oscillating, how are we sure that it is confined?
The oscillating and confining is two different. Let's say this is your confinement volume. But nobody said that you have to sit on this chair, you can run from this wall to that wall. That is oscillation. Yeah. Like for example, let's take a simple example. This is an astronomy institute in planetary motions. So the planets are like our Earth is rotating around the sun. Is it confined or not? Earth is confined or not? It is confined across the sun, but it is oscillating. Actually, for anything, if you want to confine, then it has to oscillate. It cannot just stay constant, it will fall down. Anything, for any particle, if you have to confine, it has to rotate. And rotation means it's an oscillating. You can plot it in terms of a cosine function. Right? Okay, so then there are different kind of ion trap geometries. I mean, it's just a geometry. One can choose to make different kind of traps, and we will show some of it today in the lab. So let's forget it at this moment. Now let me pictorially tell you how this. I mean, I have explained you the ion trapping. I have explained you the laser cooling day before yesterday or maybe on Friday. Sorry. So these are the things which are used for building a clock. I will go a little bit quicker here. So what you do, you produce some neutral atoms from an atomic oven, which I explained during the time of fountains and so on. Then you use some photoionization technique, that means stripping, using the laser beams to strip out one of its valence electron, then it becomes iron. Then once it becomes iron, then you apply, okay, by the way, these are the electrodes. These are the electrodes where you apply the electric field. So you apply the correct electric field, then ions will be trapped. Okay, by photoionization, this becomes iron, then ions will be trapped. But then there will be multiple ions. You want one, because you don't want the Coulomb shift and everything. So what you have to do, you have to detect the signal, which is called fluorescence again, from these multiple ions, and the signal will be at some level. If you have n number of ions, then the signal will be corresponding to n number of ions. Then let's say you do some mechanism to reduce the trap potential little bit, and after a certain point, if you keep on reducing the trap potential, after a certain point, the n number of ions cannot be stay in that trap. Right? They have enough Coulomb repulsion among themselves. So your trap has to be stronger enough to overcome this Coulomb repulsion. Right? If your trap potential reduces, at some point it will not be strong enough to keep all these n number of trapped particles, because they have lots of Coulomb repulsion. It's very strong. So if you keep on reducing, at some point you will see that one ion will be gone out of the trap. And then what happens to the signal level? Signal level will come down. Right? The signal corresponds to 4 ions is different for signal corresponds to 3 ions. Right? You keep on doing that thing. And at some point, your all ions will be gone. And then you will reach to the noise floor. That is your dark count. You get PMT, dark count, etc. So like basically you have no ions, so you have no signal from the ions, you are only detecting the dark background. Okay, so then this way you calibrate your system. These steps are calibration. So you know this is my dark count, and this level corresponds to my single ion. So next time you do the same, repeat the same thing, and you just stop here. When you reach to this level, you know that I have a single ion, so I have to stop here. I want to use that. Okay, that's how you basically have a single trap ion. Then okay, this is fine. Then you use lasers for laser cooling them. You have to use multiple lasers to cool them, because these ions are still hot. Okay, you have to cool them to some millikelvin temperature. Then once it is cooled, it is ready for clock. The sample is ready. Then you drive the clock trans. Okay, this little you forget about that. Then you drive the another your this very narrow line with ultra stable laser. You shine it on the iron, and you drive the clock transition, and then you basically do all this rest of these things which I described to make this clock operation. So this is a pictorial representation of the track time clock. Now I will go to the neutral atom thing. Is there any questions so far? Anything? Okay. If not, then let me go to the neutral. Yeah. Yeah.
There we are seeing the mathematical thing. So there is a term called minus 2z.
Minus?
Minus 2z.
Minus?
Minus 2z.
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 2z. Okay, which one is that?
Before. Where you wrote down the expressions.
Yeah, I'm coming to that. This one?
That's
Huh?
one slide.
Back. Yeah.
Which one?
That equation of motion.
Yeah. Oh, so okay, let's go into that. So basically, you see this alpha and beta. So this alpha and beta are factor of different, and that's why this minus 2 comes. So it's basically it says along the z direction your track is your electric field is 2 times smaller compared to the amplitude of the electric field in the radial direction. So there is a factor of 2 different. Now why it is the case? That comes from the symmetry. Then I have to really go into, but it's just simply saying there is a factor of 2 strength-wise difference along 2 different directions.
And is it the force in different directions?
No. Actually, what happens? See, if a force is a vector, yeah, and it has components along, and x, y, z is an arbitrary direction, right? You can rotate the x, y, z axis as you want. So now what happens? If you take any force, it will have an x component and z components if you divide it into 2 parts. Okay, just take 2-dimensional thing. So any force will have an x component and z component. Similarly, any force, another force pointing in a different direction will have a y component and a z component. That means both of these forces are giving z components, right? So along the radial direction, any force will have an x and z component or y and z component. That's why z component gets twice. And due to the radial symmetry, x and y direction is constant. So z component is getting, has a recurrence factor from both of these things. That's why you take your z components factor of 2 lower. Okay, so you can do this little bit mathematics and you will find the same. And that's exactly why there is this factor of 2. Otherwise, if you don't take this factor of 2, then in z direction it will be twice force. Okay. Okay. Yeah. Now I am coming to the neutral atoms. Okay. In case of neutral atoms, what did I say? That you not necessarily you have to have single neutral atom, because there is no Coulomb repulsion, there is no force between the neutral atoms. So neutral atoms can be many. It can be several thousands or even more than that. Okay, but you start with again magneto-optical trapping. Yeah.
Also in the ion case, don't we have to consider the quantum tunneling effect since we are considering only one?
What is quantum tunneling?
Because the potential we are trying confine it in the box, like we can for when because of the potential.
Yeah.
Wouldn't it get enough? Like we do have a probability
of it to what? Please complete it. Otherwise, quantum tunneling is a very fancy, nice word nowadays. Everybody wants to do quantum. But what is quantum tunneling?
And like, doesn't it have a non-zero probability to be out of the confinement?
Oh, everything has a you also have a probability to be in the moon at this moment. But what is that probability? That tells everything. But that probability is extremely small. And why it is too small? See, everything has a quantum tunneling or a quantum effect that, I mean, I am physically here right now, but I'm probably also physically in Calcutta right now. So, what do I have to do to increase the effect of other things? Okay, then just forget about that at this moment. Maybe we can discuss it separately. Okay, so let's come to the neutral atoms. First thing what you have to do, you have to collect lot of neutral atoms. You have to trap them, pull them. And what technique do you use for that? What technique do you use to collect lots of neutral atoms, confine them and pull them? Magneto-optical trap. And that's what is this red things are showing basically. I already described that very well. So you first start with magneto-optical trapping, collecting lots of neutral atoms, and then you use another focused laser beam, very intense laser beam, focused at the center of this trap, and create a lattice structure. And I will come to that what is it, but basically it looks like, have you seen the egg cartons? Eggs in two-dimensional things where the eggs are sitting in the egg carton. So if you just think about the carton, not about the eggs, you can create a potential which looks like this egg carton in a two-dimensional array of periodic potentials. And the eggs are your neutral atoms. If you place them, they will be placed at the minimum of each of these potentials. So using these laser beams, you can create such kind of structure in the lab. And then you can trap your atoms at the minimum of all these potential arrays, and that is called optical lattice. So this is a lattice structure. You have read it in some of your solid state physics books, detail or something like that. So this kind of lattice structure you create, but here you create with the help of laser beams in a very small dimensions. Okay, so how do you create that? Well, for potential you have to have some field and then force to trap them. So if you take a laser beam and if you look into its cross section, you know what would be the intensity profile of the laser beam in an ideal case. Assume there is no higher order effect. Gaussian. So the intensity distribution of a laser beam, if you take cross section, intensity distribution is always Gaussian if there is no higher order effect or very high part of laser beam system. Now this is what the Gaussian gives us. This is the waist size, and this is radial change, and this is the basically power. Now you focus that laser beam. This laser beam is using this lens. You focus it. Why do you focus it? Because you want to increase the power at that focus point. And that's why you focus. If you have enough power, then you don't focus. That's not so important as before. Then again atom, and I like you have some questions, sorry. Oh, okay. So atom, let's say it's a two-level structure, ground state and excited state. In an intense laser beam, or let's say in any laser beam, these two levels will have some perturbation. And from where it will come? Yeah, so what is that effect? Huh? Electric field is? Yeah, that's right. And what is that interaction? You are right. Huh? Stark effect. Yeah, so it has some polarizability. Atoms, the states have some polarizability, and that will interact with the electric field of the laser beam. Why it will not interact with the magnetic field of the laser beam? It's an electromagnetic wave. Because magnetic field strength is extremely small. It is a factor of C. Right? So magnetic field effect will also be there, but that's really very small. So that's why we are not considering. Okay, so that means the ground state and excited state will be parted. Parted means will have shifting, but the shifting, if you plot, will be something like that. It's not that two states just shifts like that or like that. And this is like position. What is this position? This is the Gaussian laser beam. So this is set 0, this 0 is center of the Gaussian laser beam, and this is increasing radially in both directions. So if your atom is at the center, it will have maximum shift, maximum perturbation, because your intensity according to Gaussian this thing, you have maximum intensity there, and as you go out from the center, your intensity level goes down. That's what is plotted here. That means your maximum shifting will be for the atoms which are at the center of this Gaussian laser beams, and it will be more relaxed as you go out of the on the sides of this Gaussian laser beam. But both state will have some shifting, and that is what correctly she pointed out. This is this start shift, and energy level shift you can write in second order perturbation theory, and this is this interaction. This is this E is the dipole moment, electric field, divided by all these things, and if you do a little bit more mathematics, it will be written in terms of Rabi frequency, and the Rabi frequency square is proportional to the intensity of the laser. So practically, forget about all these things, your shifting will be proportional to the intensity of the laser. And that's what I just explained. Your intensity is maximum at the center of the Gaussian laser beam, that's why your shifting is maximum, and your shifting is lower there, so here it will be less unperturbed. Okay. Okay, so this basically now creates, once it is this kind of perturbation, then it itself will create a trapping potential. So far we just spoke about the shifting, but if you now look into it three-dimensional, so if you somehow create so this Gaussian laser beam I told you in 2 dimensions, it's a cross section. But if you have 3 perpendicular laser beams in such a way, then basically you can create a 3-dimension this kind of potential. Just rotate these in 3 dimensions. Okay, you have to use your lasers in such a way, let's not go into the technical detail, in all 3 dimensions and etc. Then you can create a 3-dimensional potential, which is like this egg cartons periodic potential. That's how we create there. But the basic is basically start shift. So again you see, you have all of you have read the start shift, but this is an application. So whatever you are reading during your BSc, MSc level, these basics are very, very important. Rest is how do you apply it in the lab. If your basics are clear, it's only like trying to use it in the lab, and that part is actually not that difficult. Basics has to be very clear. Okay, this part I am just forget about that part. Okay, so this basically says that this it will create this kind of periodic potential, and the potential will have some depth and etc. And this potential, since it's periodic, with some mathematics which I am not going into detail, it will be a sine square function. You have to do little mathematics, let's forget about that. So the lattice potential, if you write it in mathematical form, then it will be some sine square function. It is proportional to omega square. Omega square is proportional to intensity of the laser. That means higher the potential depth, if you take very large and large intense laser beams. Okay. This is just a pictorial representation. This is basically this egg carton which is shown, and these are the starts. The energy level can, depending on the sign of the polarizability, let's say these are 2 unperturbed states. It can come closer to this, it can go away from each other, or it can go in the same directions, right? Depending on the sign of the polarizability of a particular state. The shifting direction or shifting amount, it will be higher energy or lower energy or whatever it is, depends on sign of the alpha. Alpha is the polarizability. Okay. Now, think about the clock transition. This is the clock transition, for example, in some particular case, for some particular atom. So, due to this intense laser light, these 2 states will shift. So, that means you will not be able to see the unperturbed transition. Your transition frequency will shift, right? That's what you don't want. So, what you have to do? If you follow these things, like due to this external very intense laser beam, both of these states will shift. So it's not necessarily that both of these states are shifting by same amount and in the same direction. It can also shift in the two opposite direction. It can shift in the same direction, but in different amplitudes and etc. But the point is, by all of these things, you will see the shifted frequency, perturbed frequency. That's what you don't want. So for that, you have to. This is the polarizability. Forget about the details. I mean, polarizability has different components: scalar component, tensor component, vector component. Let's not worry about that. You have to choose. Okay, so the point was, you cannot forget everything. The one part you have to forget about these parts right now. But let's just consider this scalar component. This polarizability is frequency dependent factor. So polarizability depends on a particular state, and for a particular polarizability also depends on frequency. There is a DC component of the polarizability which is independent of the frequency of the laser, but there is an AC component of the polarizability. That's why you see DC start slip and AC start slip, right? Have you read that? Okay, start slip. So there are two components of the start slip. There is one thing is called DC start slip, which is depends on the DC part of the polarizability, and the AC start slip depends on AC part of the polarizability. That means it depends on wavelength or frequency of the light you use. So there are certain frequency or wavelength of the laser where these two energy levels will shift in the same direction and by exactly same amount. Yeah. So it just happens in few cases. There are few wavelengths of the laser or few frequencies of the laser. Frequency and wavelength is just inverse proportional to each other, where the polarizability of the both these states becomes same and they have same amplitude in the same direction. Polarizability of both states are exactly identical, and that wavelengths are called magic wavelengths. If some magic happens, it's nothing magic happens, this is just normal physics. Then what happened? Then what happened? Let's say these are two original states, ground state and excited state. Both of them have shifted in the same direction, this delta E. This is the shift at some particular frequency of the laser light and in the same amplitude. So then what happens? This perturbed state, this frequency difference between these two perturbed states is exactly same as unperturbed frequency, right? This has gone down by delta E, this has gone down by delta E. That means the frequency, transition frequency between these two states is same as transition frequency of this. Dotted blue line and solid blue line is same. Agreed? The simple thing, right? And that happens only on certain frequency or wavelength of the laser, and those wavelengths are called magic wavelengths. This was first demonstrated by Takeyoshi Katori in Japan, and he is like a pioneer of this entire magic wavelength. That actually opens up a lot of possibilities. Okay, let's not go into that, but he is a godfather of that thing. Now, in a nutshell, we have described the fountain, which was this blue, and so blue one was the what was blue one? What was blue clocks? These are the room temperature operation microwave clocks, and these green ones are the fountains, which are laser cooled microwave clocks. Then on top of that, I am plotting this yellow and this cyan, and these are these two types like ion clocks and neutral atoms clocks. So the cyan ones are the neutral atom clocks done by different groups. You have some questions? Oh, I thought you were raising your hand. And these yellow ones are different ion clocks, and you see that best fountain accuracy has stopped here. It's like 1.6 times 10 to the power minus 16, 1.4 times 10 to the power minus 16. Whereas these ones have gone to 10 to the power minus 20 level fractional accuracy, 4 orders of magnitude better. And what did we say? That delta nu by nu zero is like 4 to 5 orders of magnitude higher in optical frequencies. That's why you expect 4 to 5 orders of magnitude better enhancement insensitivity, and that's what is like I have plotted all the clocks, microwave or optical clocks in the world, and this is so far where it has reached. Now, this is sort of how this entire field has started by whom? Rabi in 1945. He got Nobel Prize in 1944. And this is sort of until sort of, let's say 2022 day and what is expected for it about 2026 one, how this field has gone further and further. Ramsey was Rabi's student, PhD students. So he took it over and then actually developed this Ramsey spectroscopic techniques, which I described, these two cavity, fabricated cavity, they are interfering and all these things. That is Ramsey spectroscopy. He developed these things. And then using that, first cesium clock with room temperature was demonstrated in 1955 by Essen and Perry. And soon after, in 3 years, it was commercialized. And since then until today, it's exactly same cesium clock is available. Only the packaging and company has changed. But practically it's same thing which is still commercially available. Then the laser cooling technique was developed in, it's actually developed during the time of 1978. See, during this time there was no laser. Laser came during 1960-65 around that time. And people did not know what to use. I mean, is there any usefulness of the laser? People just thought, okay, maybe one can do shine the lasers on sky and do Star Wars kind of thing. But today the laser has changed the entire world. It's used in everywhere. And laser cooling technique was demonstrated during 1970 etc. for an iron and etc. But actually the laser cooling prize, is it written there? William D. Phillips at NIST, he got the Nobel Prize for laser cooling. Steve Chu, Bill Phillips, and what was the third one? And I was actually working with Bill in my postdoc. So, and then using that in 1993, the atoms were laser cooled and fountain clocks were developed. Okay. And first optical clock was demonstrated in 2001. So it's like, let's say 20 years back. And since then, the optical clock has improved and got improved, and today it's almost 10 to the power minus 20 order. It has reached to 10 to the power minus 20 order, fractional accuracy. Okay, now the next slide will tell you how many Nobel Prize winning technologies are being used in atomic clocks. There are 12. So, for example, I told you about Rabi, then Ramsey, Bill Phillips, and all these these three gentlemen, they got Nobel Prize together for laser cooling in 1997. Then recently, the most recent one is David Wineland. He got Nobel Prize for ion trapping and using it for quantum processing and etc. etc. So this probably tells you two things. One is how complex are these technologies. Okay, because there are already 12 Nobel Prize has gone different techniques which are used in different clock things. And how important is that field? Because people are just keep on trying to improve these things, and next one will be probably nuclear transitions, which I just mentioned briefly. So there is no end to it. Because there is no end to it, because there are a lot of applications. Okay. So the next time, tomorrow, I will talk to you a little bit about pairs. Why do we need that kind of so accurate optical clocks? Why do we need it? It's not for coming to this summer school, or it's not for the simple application. But it has certainly lots of needs or importance. That's why they're trying to improve its accuracy better and better. Okay. So I stop here. If there are any questions, please ask me. Yeah.
So how would nuclear transitions have a higher, like how would it be better than
okay, good question. See, an electron gets easily parted up by an electric and magnetic field, external electric and magnetic field, because electrons are in the outer cells, but the nucleons are in the inner cells. So electron के अंदर है. So the perturbation of this external perturbation, electric magnetic field, like Z1 star shift, is extremely smaller for nucleus. Okay, and that's how now we are reaching to a limit where we have to think of that 10 to the power minus 20. This bringing to the limit that now even just stabilizing the electric magnetic field is not enough. We have to choose a system where these perturbations, like let's say this polarizability or this magnetic field that Z1 shifts, are even smaller or basically negligible for some such systems, and that is only possible in nucleus. Yeah, that's why the nuclear transitions will be much better clocks compared to the electronic transitions. But driving the nuclear transitions are extremely hard. Any other questions? But one thing I just wanted to tell you that what is your impression? You might think at this moment, because you are just reading books, BSc, MSc levels, you think, oh, this is so complex, how can I do that? No, it's like people like you, those have actually have done all these things. So it's complex, but it's doable. It just needs some interest. If somebody have interest that I want to work on this thing, then it is not complex. And you have to please clear your basics. Please, I mean, this is the right time, BSc and MSc, this is the right time when you can clear your basics, and also PhD someday. But actually, when you go to PhD, you won't have that much time to read basic books. Then you have to apply them. So please don't waste time, read the basics, forget about all this. I mean, you will see some people are always trying, oh, I have to do a project here, I have to do a summer project there. Those are not that important. Believe me, those are not that important. Clear your basics. If your basic concepts are clear, then you have a lot of time to do research. See, I can tell you most of the people in your BSc, MSc levels, they are trying to do project here and there. What is the main reason? Because they want to get a recommendation. Frankly speaking. In 1 month project or 1.5 month project, nobody learns a lot of things or nobody publishes a paper. It's impossible. Yeah, so the only thing they want to, I want to apply there, I need a recommendation letter, I can get from that guy. We are doing it. We are writing hundreds of such recommendations. You know. But see, if you do good, a recommendation letter cannot stop you. If you have one recommendation letter less, nobody can stop you. I am guaranteeing you. But please I mean, you do project. Nobody is stopping. I'm not saying you should not do project. But even if you do project, please try to learn. Learn a little bit, but please learn. You don't need to learn a whole lot of things. Learn a little bit, but please make sure your basics are clear. If your basics are clear, then nobody can stop you. But if your basics are not clear, you can go up to certain level, but then you cannot grow further. You cannot think yourself. And research is something where you have to think yourself. Your supervisor tells you, oh, count this number of balls, I will ask you in the evening, and you count that in the entire day, and your supervisor comes, okay, then I count 10. That is not research. Research is something you have to like think yourself. You have to, there will be problems, and don't expect your supervisor to know the solution of the problem. Then it is not research. In most of the cases, he or she doesn't know the solution of the problem. That's why we have researchers, not laborers. I tell it to my own research scholars also. They are sitting on the back. So think, what are the solutions? How can you solve it? And not necessarily that all solutions will come from you. It's impossible. We are all human beings, and we are not Einstein. But then discuss among groups, among other people, etc. So if you have research interest, if you want to go into academics or etc., if you want to do research in the future, make sure your basics are good. Then only you can do a good research. Otherwise, it's like, okay, there are a number of people doing PhD, there are a number of PhD theses, they publish a lot of papers, but practically they're all useless. Yeah. Okay. Are there any online questions? Sorry, I forgot to ask.